Hey everyone, and welcome to this explainer. Look, if you're a BCA first semester student and your computer architecture syllabus is feeling like a completely foreign, overwhelming subject right now, take a deep breath. You are in exactly the right place. Today, we're starting from absolute zero. We're going to map out the entire first unit of your syllabus together. Our goal here is simple: give you a crystal clear, confident understanding of the big picture. We want you to see exactly what each topic is and why it actually matters, way before you have to dive into all the grueling math and complex derivations. Okay, let's just get the lay of the land. This beautifully outlines our entire journey for Unit 1. We're going to travel all the way from basic number systems like decimal and binary, right down to the physical digital logic circuits that actually power our machines. Think of this explainer as your map of the territory. By the time we're done, you'll know exactly how all these seemingly disconnected pieces snap together to form the true foundation of computer architecture. So here is our roadmap for today. 1. Speaking the computer's language. 2. Math tricks for hardware. 3. Codes, errors, and text. 4. Inside the digital computer. 5. Gates, hardware building blocks. And 6. Simplifying the circuitry. To make this super digestible, we're actually going to split this explainer into two distinct halves. Part A covers the language computers use to represent data, that's sections 1 through 3. Then in Part B, we're going to explore the physical brain that processes all that data, covering sections 4 through 6. All right, let's jump right into section 1, speaking the computer's language. It all really starts with one massive, fundamental question. How in the world do we bridge the gap between abstract human numbers, the numbers you and I use every single day, and cold, hard, physical, electronic hardware? Well, this is exactly why binary is the natural language for computers. We humans use base 10 decimal, right? Probably because we have 10 fingers. But a computer, at the microscopic physical hardware level, a computer is just made up of billions of transistors. And a transistor really only has two stable voltage states. It's either switched on or it's switched off. That's it. And those two physical states map perfectly onto base 2 binary, which only uses zeros and ones. Of course, since we don't naturally speak in zeros and ones, we need a reliable way to translate. Converting our decimal numbers into binary is actually as simple as just following repeated division steps. You take your whole number, divide it by the base, which is 2, keep the remainder, and rate it back. So say you want to convert the decimal number 13. You just repeatedly divide by 2, which gives you remainders of 1, 0, 1, and 1. Read those backward, and boom, 1101. Now what about octal, which is base 8, or hexadecimal, base 16? Honestly, you just group the binary bits together. 3 bits make an octal digit, and 4 bits make a hex digit. They're really just clever shorthand systems for us humans, because writing out massive long strings of binary is incredibly painful. And once you can convert these numbers, you can do math with them. Now, please don't stress about the deep math right now. Just know this one golden rule. Binary, octal, and hex arithmetic follow the exact same logic as the decimal math you've been doing since grade school. Addition, subtraction, multiplication, division, it all works the same way. The only difference is the base point for when you carry over to the next column or borrow from it. It's the same game, just a different set of boundary lines. Let's move on to section 2, math tricks for hardware. So here is a crucial reality of computer engineering. Physical hardware components are expensive. Every single custom circuit you build takes up valuable physical space on a microchip, and it costs real money. Which leads us to this incredibly fascinating logical puzzle. How do you subtract numbers if you absolutely refuse to pay for a dedicated subtractor circuit? The secret answer lies in something called complements. Every number base out there has an r's complement and an r minus 1's complement. For our binary system, that translates to the 2's complement and the 1's complement. Basically, complements are this brilliant mathematical workaround that lets us trick a simple, cheap addition circuit into doing subtraction for us. Instead of building separate, costly subtractor hardware, the arithmetic logic unit simply adds the complement of a number. It is a massive, elegant hardware simplification. And engineers have other clever tricks too, like BCD, which stands for binary coded decimal. Instead of converting a whole massive decimal number into one giant binary string, BCD just encodes each individual decimal digit into its own neat little 4-bit group. But there's a catch here. 4 bits can technically hold 16 different values, but decimal digits only go from 0 to 9, right? That leaves 6 totally invalid patterns. So when you're doing BCD addition and your result accidentally hits one of those invalid patterns, you have to manually add a correction factor of 6 to fix it. This is a vital little quirk, and you're actually going to see it pop up again later in your syllabus when you study the 8085 microprocessor's DAA instruction. That instruction exists for one reason: to completely automate this exact BCD correction in the hardware. All right, moving to Section 3, Codes, Errors, and Text. Beyond just representing standard numbers, computers use highly specific codes to solve specific physical hardware problems. For example, we use decimal codes like XS3 for specialized math. But let's look at gray code. It's fascinating. In standard binary counting, multiple bits might flip all at once, like when you count from 3 to 4. But gray code is designed so that only a single bit flips between any 2 consecutive numbers. Why does that matter? Because it brilliantly prevents hardware glitches in physical mechanical components like rotary encoders, where having multiple bits change state at the exact same fraction of a second can cause massive errors. Speaking of errors, what happens when things go wrong? When data is zipping through memory or flying over a wire, bits can accidentally flip from a 1 to a 0 just because of random electrical interference. To handle this, we use parity bits. A parity bit is just an extra bit tacked onto a message that acts as a simple alarm system to detect if a single bit error happened. But if you want to be bulletproof, you use the mighty Ham encode. By mathematically placing multiple parity bits at specific power of 2 positions, Ham encode can't just detect an error, it can mathematically pinpoint exactly which bit got corrupted and physically reverse it. It's basically self-healing data. And of course, computers don't just crunch raw math. They need to read and display letters. This is a great look at how text encoding has evolved over time. We started with the strict limits of 7-bit ASCII, which basically gave us 128 standard English characters. Then we moved through IBM's 8-bit EBCDIC for the old mainframes. And finally, we arrived at the incredibly flexible variable width Unicode that we use today. Unicode is a total game changer because it exists to support essentially every single human language, alphabet, and emoji on Earth. Okay, that wraps up Part A. Now we cross over into Part B with Section 4, Inside the Digital Computer. Every single digital computer, from your smartphone to a massive supercomputer, operates on the exact same foundational architecture at a block-level view. It's literally just data flowing through 5 distinct physical areas. You have input, memory, the ALU, which stands for Arithmetic Logic Unit, where the actual math happens, and output. And every single piece of that flow is fully coordinated by the central control unit. Honestly, everything else you are going to study in this course is really just zooming in closer and closer to these 5 specific blocks. Let's zoom in right now, actually, with Section 5, Gates, Hardware Building Blocks. Deep inside that ALU we just mentioned, the actual physical computing is performed by logic gates. These are literally physical transistors in action on a microscopic scale. The foundational gates are AND, OR, and NOT, alongside a couple of others you'll encounter like XOR and XNOR. And those truth tables you see? They aren't just math assignments. They define the absolute unbreakable logical rules for exactly what output voltage you will get from these gates based on the inputs you feed them. If you can understand these simple truth tables, you basically understand the foundational logic of all computer hardware on the planet. Now, pay special attention to the concept of universal gates, specifically NAND and NOR gates. They get the title universal because a single one of these gate types can be wired up to build literally any other logic function, including AND, OR, and NOT. This is a massive deal for manufacturing. Building a computer chip entirely out of just NAND gates or just NOR gates is incredibly efficient for a factory. You literally just mass produce one single type of microscopic component and creatively combine them to mimic everything else. Which brings us to our final stop, Section 6, Simplifying the Circuitry. So before an engineer ever touches a soldering iron or prints a silicon chip, they have to optimize. Instead of blindly building a massive, messy, and insanely expensive circuit, they use the mathematical laws of Boolean algebra to drastically simplify the logic expressions first. You'll learn laws like the commutative, associative, and distributive laws. But the absolute star of the show here is De Morgan's theorem. It is arguably the single most powerful tool you have for converting and minimizing logic gates before you spend a dime building the hardware. But listen, if you are anything like me and you absolutely hate writing out lengthy, tedious algebraic equations, Karnaugh maps, or K-maps, are going to be your absolute best friend. K-maps take all that messy algebra and turn it into a highly visual grid.
You simply take your truth table, plot the results onto this grid, and then you just mechanically group the adjacent ones together. By just circling these groups, like circling a pair of ones right next to each other, you instantly eliminate variables. You can read a perfectly simplified circuit expression right off the page without doing any of the heavy algebra. It is so incredibly satisfying.
And with that, we have officially wrapped up our map of Unit 1. We've covered the fundamental number systems, the sneaky math tricks to save hardware costs, the physical logic gates, and the visual simplification methods. But all of this leaves us with one massive, incredibly provocative question for our next explainer. Think about this. All these basic logic gates we just learned about, they only react to their present inputs in the moment. So how in the world do we build sequential memory circuits that can actually remember their past states? Well, that is exactly what you are going to tackle in Unit 2. Until then, keep learning, trust the process, and I'll see you in the next explainer.